even further back, why would you want antibodies? Well, it's because you have bodies. And I've discussed what that means is the word bodies is just molecules that exist in a body. So it's interesting. People say DNA is the molecule of life. Well, yes and no, but most of what our genome does is produce, regulate, and control what proteins are in your body. So it's fair to say, and that's what I believe protein means life, basically. It's some Greek term like that, I don't know. It is actually the role of DNA to store the information that can produce the tens or hundreds of thousands of different proteins, each of them at different levels that make up your cell. So basically proteins are life, and that's an interesting point. And what's fundamental is a given species or organism is defined by its set of proteins. And the levels of those proteins can and should change at a given time. But clearly, which proteins exist do not change. That's what cancer is. Cancer is mutations in your DNA, but it's well recognized those mutations change a protein. So evolution gives us a set of proteins at birth, and we use them to control our cellular biology. And if they're changed, you get cancer. If there's not enough of them, you get degenerative disease. So it's very important that your set of proteins remain stable, are regulated correctly. If not, that's when bad things happen. So if you have proteins, it's fine if you never have a disease. You can go for decades. Yes, so as I've said, to understand what antibodies are, to understand what a body is, and that was these proteins that control life. It's what the cell is actually made of. And what's amazing is any organism is defined by its proteins. That's just the way it is. So what has always amazed me, as I said, in any species, the proteins must remain the same, the genome must remain the same. So you have humans have 20-something thousand proteins. Other species have less or more. But one of the main goals of, there is a goal, it's not thought out, evolution in biology is don't change too much. So that never changes. But as I said, what's amazing is Paul Ehrlich discovered to fight invaders, which have their own proteins, you must be able to mount a response, now called the immune response. And that's what antibodies are. Anti means against a body. So a foreign body, which we now know is made of proteins. And I'll say it again, what amazes me is the proteins that make up your cells must not change. But then you have the immune system, which generates antibodies. And that's the exact opposite. You have billions of different ones at any given time. And within days, if one of those, and this is what the immune system does, which is amazing, recognizes a foreign invader and neutralizes it, that can grow by thousands of fold. So you can have one antibody that is useful because it's neutralizing a virus, and within days or weeks, it is becoming a part of your blood. It's floating around. So suddenly, proteins don't change except for this one critical time when new ones can arise within days. And that's what I found amazing. And the amazing breakthrough that came in the 70s was proteins are encoded by DNA. For any antibody, Cesar Milstein found a way of isolating the DNA and thus the antibody for a given function. So suddenly you could take any natural antibody and produce it outside the body. But it was still a natural antibody, you couldn't make new ones. But suddenly you could say, why does this virus get neutralized in this human? Well, it's because of this antibody we isolated. Why does this happen? So suddenly you could find, purify, and analyze individual natural antibodies and use them. And that went on until the 90s, when recombinant DNA became run-of-the-mill, and that's when I started doing research. And the amazing thing we decided to do, we being the scientific community, is if we now know how antibodies naturally work, and we can make synthetic DNA, can we just make what we call synthetic antibodies? They look like natural antibodies, but the difference is we designed every residue, i.e. every amino acid, every component ourselves. And what synthetic antibodies did was several things. One is, of course, anything that's synthetic is more reproducible. You can make larger quantities. You can fine-tune how it works. But importantly, and this is a critical thing, synthetic antibodies opened up any protein, including human proteins, as targets. Because I'll point out one other key point. One thing natural antibodies should never do is target your own proteins. So we have ways of preventing antibodies arising from our body to target our own proteins. And that's a limit, because if cancer is caused by your own proteins, you can't get natural antibodies to target that. So once we could make synthetic antibodies, we could suddenly open the door to targeting any protein of interest, whether it's our protein or a foreign protein. Milstein in 75 or so allowed us to isolate individual natural antibodies. So you could look at them. Suddenly you could say, hey, you know what? And all proteins are encoded by DNA. So you could actually get the DNA of individual natural antibodies. And of course, if you're going to understand anything, the first thing you have to do is to be able to look at it. So suddenly we could look at hundreds and then thousands of natural antibodies. Why does this one do this? Well, it looks like this. Why does this one do this? It looks like this. But of course, that's all kind of cataloging. The other two big breakthroughs were DNA sequencing, which, I don't know, just by luck happened with this guy named Fred Sanger in 1975. So the first time, not only could you isolate DNA, you could sequence it. So if you get a DNA that encodes an antibody, which Milstein allowed, you could make that antibody and study it. And crucially, with Sanger's technology of DNA sequencing, you could encode the DNA that encodes it. And the central dogma is DNA makes mRNA, which people heard about in the vaccine era. But mRNA makes proteins. So the beautiful thing is, if you can get the DNA sequence, you get the protein sequence. That's the one-to-one correlation. So suddenly, with Milstein's technology, you could isolate individual natural antibodies for analysis. With Sanger's technology, you could sequence the DNA and thus also get the actual sequence. And it literally is that. It's the molecular, these are large molecules, but you get the complete sequence of what this antibody is. And then the other big advance was not DNA sequencing, but DNA synthesis. That's where the word synthetic comes from. And that, interestingly, was a lot of researchers, but this guy Gobind Khurana, who even worked in UBC for a while, he developed, along with others, the ability to make DNA synthetically. So suddenly, let's recap. Isolate and look at antibodies, Milstein. Sequence DNA and thus the protein of natural antibodies, Sanger. And then Khurana enabled, great, now not only can you look at these things, not only can you sequence and know what their structure is, with synthetic DNA you can start changing it. So that was the big third advance. Now if you think this antibody works because of this part of its sequence, you can change it. You say, oh, I think it'll work better if I make this part of the antibody this instead. And suddenly you could make individual synthetic antibodies. And that's how it started first. You had to make them one at a time. But a big fourth advance, which is more getting to my area in the early 90s, was a phage display technology with George Smith. And each of these rightfully has a Nobel Prize, by the way. George Smith developed a way, hey, you know what? You can make individual antibodies, trial and error, but most of them fail because they're complicated. George Smith developed a technology that allowed you to make 10 billion different pieces of DNA that turn into 10 billion different antibodies that are all represented in a milliliter of solution. And suddenly you've made 1 billion different synthetic antibodies rather than one at a time. And if you have 1 billion shots at goal, you are much less likely to be wrong. So if you put those four things together, isolating antibodies, Milstein, sequencing antibodies, Sanger, synthesizing DNA, thus being able to make synthetic proteins, Karana, and then finally George Smith, rather than making one protein, does this work? No. Now make another protein 2 weeks later, does that work? In 2 weeks you can make 10 billion proteins. And in another week you could just say, which of these ones work? Forget the ones that don't. So if you put those four Nobel Prize winning things together, you went from knowing nothing to knowing what natural antibodies look like, to knowing what their molecular structure is, how to alter their molecular structure one at a time, and then finally to alter it 10 billion at a time. And that was exciting to me because I was just finishing my PhD when the last technology came out, which allowed us to make billions of synthetic antibodies. And within a week, take any protein of interest, say, you know what, I think cancer of the breast is caused by a protein called HER2. In the old days, you couldn't do that much with that. But when you could make antibodies, you could isolate antibodies that bind HER2, and Herceptin came out of that. Suddenly, not only can I know which protein causes a disease, I can make, as I said, a protein is a body, and cancer is in some ways like a virus. It's an invader. The difference is a virus is completely foreign. Cancer is one of your own cells becoming invasive. It overgrows, it moves where it shouldn't be, metastasis. But really it's an invasive organism generated by you. And in the old days, you could understand which proteins are causing cancer. But knowing what's causing it doesn't mean you can cure it. But suddenly within weeks, you could develop antibodies against many of these cancer-associated proteins. So, and this is getting into our era, late 90s up until now, every time we know that there's a protein that we think causes a disease, cancer, neurodegeneration, very rapidly we can develop a synthetic antibody that hits that protein. And suddenly you have a potential drug. So you go from not being able to do anything to be able to, this testable hypothesis. You make an antibody against the protein that you think is the problem. You put that into cell and animal models. And within months, you can know, yeah, I was right. This could be a drug. And because it's already designed by you, we've done examples, others obviously. You can make kilograms of that drug, which could treat tens of thousands of people, again, within months. So those are the advances that went from just kind of knowing from Ehrlich, who also won a Nobel Prize, the conceptualization, to knowing what they look like, to knowing what they look like in detail, to being able to alter them one at a time, then to alter them at 1 billion at a time. And then now we have manufacturing plants in every major country that can within a month or two make doses for hundreds of thousands of patients for any design you can come up with, the antibody. Yeah. So you're making 1 billion different antibodies in their sequence, which means their structure and thus their function. And most of them will do nothing because, they exist, but they don't perform a function. But if you have a billion, and we've shown this endlessly now, and others have, there's always 1, 2, 10 that do what you do want to do, and we have ways of then rapidly getting out of the billions. The one different antibody that binds this protein prevents this pathway and could be beneficial for this disease. You know, we did it with COVID. COVID uses a particular protein to get into the cells. Well, you can make an antibody that binds that protein. Suddenly COVID can't get into the cell and it doesn't replicate. Certain breast cancers use a protein called HER2 to replicate and grow rapidly. We could make an antibody against HER2. Now HER2 can't signal for growth and the cancer doesn't grow. So you have a cancer treatment. So suddenly what you could do is take 1 billion different antibodies and within a week find half a dozen. So you're going from 1 billion to a few. And those few, because they are different in the right way, recognize the protein you think is a problem in a given disease. And then they correct that problem. And the beauty of it is, it may sound abstract, this is all real. It's a DNA molecule that makes a protein molecule. We have fermentation, which can make kilograms or even tons of it. That's the engineering and the art. That's what the library is. Different people design different libraries. Our libraries are among the best because, and believe me, Neal, even if I wanted to, this is where we'd have to spend. Look at the 50 papers we've written. That's the minutia. But that's just, as I've made the comparison before, in music or art, what makes this set of paints turn into a Van Gogh rather than a Rembrandt or a color by numbers? So that quite literally is having the ability to make 1 billion is huge. And then groups like mine have literally spent decades looking at first principles. Oh, we think that 1 billion should kind of look like this, or it should look like this. And some libraries work. So it's not all just make 1 billion and it works. So we look at natural antibodies, we look at proteins, and this is the science and our opinions, quite frankly. My group says we should design them like this, and luckily for us, our designs are good, then they work. So that would take hours just to explain. I think it'd be tedious. But that is where at least you have the ability. As you know, even with a set of 12 colors, it's amazing how many different paintings you can come up with, right? And there's 20 amino acids. So it's not that much. At the basic level, there's only 20 amino acids that make all proteins. But one person might say, we go classical, I'm Michelangelo, another one's abstract. So those are where you look at the problem and you say, and that's why we do call it is engineering. I mean, you're making 1 billion, but you're making choices. Even to get something out of there, that's where the design comes in. And literally, we're designing billions of antibodies. But with our principles, I think it should have this kind of amino acids. I think it should have this part of its surface changed rather than this part. You know, where do you put the color? What color do you put there? So that's both the science and art. But fortunately for us, once there are rules, when it works, you can know and you can reinforce those. Like, oh, that worked. And we've spent decades doing that. So that's not a quick answer, but it is an answer. So the Nobel Prizes I told you about didn't end up making drugs, but they gave us all the building blocks. What does the natural one look like? How can you change it? How do you make it changes? How do you do that? But then you still have to spend decades literally using those methods to be actually successful. Terminally evolved. So you went with 1 billion that could do anything but did nothing. In other words, 1 billion, no one molecule in that dominates. It's a mess. Not a mess, it's a mix. But the cool thing is when you get to 1, the only thing, and you don't want a drug that does even more than one thing, that's called a side effect. So when you get to 1, it's like It does one thing perfectly, and it does nothing else. And that's kind of the interesting part. I'm glad you mentioned that. Is it all, and nope, it's called terminally evolved. Say, good, now we're done. This one antibody, and by the way, that's fixed for all time. We have the sequence. We can put it on the web. We can put it in papers. That then will never change. And we're guaranteed 100 years from now, it'll always do that only one thing. It will recognize this protein and cause this protein to do this. And it will do nothing else. A virus is a physical particle. It has inside it, it has its DNA or mRNA. That's the message it's trying to get into your cell. Because once it gets that message into yourself, it's literally a program to make more of itself. But the hardest thing for a virus to do is the first step. How do I even get into a human cell? And the way it does this is this. It has a surface coat. Coronavirus is named for those little spikes that stick up. Those are proteins. The job of the spike protein is two things. Recognize a human cell through another host protein called ACE2, and then get into that cell. And if it does that, the virus goes in, the DNA or mRNA starts making the virus proteins, and you've been invaded. You've turned a human cell into a virus factory. But the cool thing is, if you can stop that spike protein from latching onto a human cell, the virus can't do anything. That's it. So it's black and white. And because the virus spike protein is a protein, let's call it a body again. That's what Ehrlich said. There's a body that's invaded. Well, we can make an antibody. And if our antibody recognizes that spike protein, then that spike protein is no longer free to recognize the host cell. So you've stopped it. So in that sense, it's literally a block. I mean, it's not that complicated. This protein on the virus surface must be free if it's going to recognize your cell and get in. If you block it before it meets the cell, the protein can't work, the virus can't get in. So it's very elegant, and that's the invasion by foreign particles. But I'll say cancer has this analogy. Cancer is always associated with mutations in the DNA, which cause mutations in certain proteins. And one of the typical ways cancer grows is a nice protein called HER2, which is a growth receptor. You need it for normal growth. But when it mutates or overgrows, that's what a cancer does. Suddenly there's too much of that growth factor or growth receptor, and that's called tumor. A tumor is simply too much growth of cells. And then it becomes basically an invasive organism, because cancer evolved from you, i.e. its DNA changed, but it was your DNA. And now it's, in a way, it's kind of like a virus. It's suddenly overgrowing, it's moving from the breast to the brain or the bone. And then, similar to the virus, if we now know the protein HER2 has become bad, it's enabling the cancer cell to invade other parts of the body, not unlike a virus. Then if we can hit HER2, can we stop that signal? And suddenly the virus couldn't invade because you blocked its protein. The cancer can't grow or metastasize because you blocked its signaling. And wonderfully enough, it works, by the way. And there's a link, by the way. HER2, the oncogene, as it's called for cancer, was first discovered because a virus subverted it. A virus actually started using it. So cancer and viruses have that common trait. They're unregulated, invasive organisms growing in your body. The big difference is cancer used to be one of your own cells, but it's become invasive. A virus is truly foreign, but they do have that. And all of them rely on particular proteins to be able to grow, invade, replicate, etc. And when you know those proteins, you know you have to stop them. And hello, let's do antibodies. And I'll say the big breakthrough with synthetic antibodies was now you can make antibodies against human proteins. Because your body obviously shouldn't make antibodies against, that's called autoimmune disease, lupus and other things. But sometimes it could be useful if you know, for breast cancer patients, having an antibody against HER2 is good. So you did need synthetic technology to really enable that on a large scale. Because suddenly proteins that are our proteins, we can develop antibodies against those. And my own group has developed antibodies against hundreds and close to 1,000 different human proteins. And we're looking at different ways of using them to modulate and attenuate cancer, neurodegeneration and other inflammation and other diseases.